table, and we got pretty far. We were not too far from being done with calculating the actual life table. And so just to remind you, for X, we generally do have a range, except that we will use the first number of that range to represent that age class. And that really makes sense, especially when you look at the first one, which is 0 to 1 year old for the squirrels. And that is all 530 were born, and so they were alive at least at the beginning of year 0. And so for the squirrels, we have year 0, 1, 2, 3, 4, and so forth. And then the second column is just the number of squirrels in each one of those age classes. We learned how to calculate and interpret survivorship. And I told you that it's in red and underlined because we're going to make a graph related to survivorship. And that's going to give us some information about the patterns that we see for this particular species. If we need to review any of the calculations as I'm doing this real quick, let me know. Otherwise, I'm going to kind of blip over them. All right. And then we talked about the fraction of the cohort that died. And for this one, for D of X, we were comparing to the original cohort number. So how much of the original cohort died between each one of these years, which we will interpret because it does make sense. But it's not the mortality that we're really interested in terms of patterns in the population. And so then we calculated QX, and that's the last thing we did. That's the mortality that we are going to graph. So that's why I have it in red and underlined on this slide. It's age-specific mortality, and so it's how many died during that specific time period. So the way we usually write it, or I usually write it, is the percent that were alive at the beginning of the year but died before the end of the year. So it's very specific to that time period, and that's where we were. Anything that we need to review in that first part of the life table? Okay, that was a really quick review. The last three columns are leading up to the final column, which is the third column out there, and that's your life expectancy. And as I said, the two columns that we need to calculate life expectancy aren't as easily interpreted as the ones we've done so far. Like the ones we've done so far, you can think about and you can get an understanding of what those numbers represent within the population. And so let's take a look at them. And so the first one is our capital LX. So I warned you, we have a lowercase lx, that's our survivorship. We are going to graph that. Now we've got this capital LX. So you make sure that you keep up with that, because the capital L is different. As you look at the definition up there, it's the average years lived by all individuals in that cohort. That's kind of weird. Weird way to look at things. And it kind of makes sense. We're not really going to interpret these numbers. You won't see an interpretation on this slide. But we do need to calculate it. And so to get our capital LX, we're going to go back, and for the first time, we're not going to go back to our original numbers. We're not going back to the end column. We're going back to the little LX column right here. Okay? And so make sure you get to the right column when you're calculating this. And then from there, the other difference is we're not using N0. The denominator on this formula is 2, and it doesn't change, it's just 2. And so what we're really doing is we're averaging. Okay, so we're averaging some of the survivorships. All right, just like we did last time, those X's you're going to replace with your time period you're interested in. And so for L0, then you're going to have L0, this is going to become little l0, this is going to become little l0 plus 1. That whole thing's a subscript, so this is just going to become L1. I did that really quick, but we spent a lot of time on that Monday. Is everybody okay? All right. So remember what I told you about how this ends up being a rhythm. And so essentially what you're going to do is you're going to take LX plus the next year's LX and divide it by 2. That's what we're actually doing. And so the first one is 1 plus 0.03 divided by 2. And then the next one's 0.03 plus 0.15 divided by 2. And the next one's 0.15 plus 0.09 divided by 2. Then 0.904 divided by 2, and so forth. And we're not interpreting it, so that's all we really need to know. It's just how to calculate it. We're not interpreting what those numbers mean. Okay? Any questions about that? how to calculate that. All right, I don't really have any checks for this, because remember we had a few checks, like here, and these two numbers should be the same, and this one should add to a 1. So I don't have any checks on this column, you just have to do the best you can. All right, so here's where it gets weird. There's no formula on this slide. And so you need to make some notes to try to make it make sense to you as to what you need to do, okay? So the first thing you're going to do is you're going to add up all of these numbers. So add up this column, the LX column, and you're going to put that number right here in that first cell. And so this is what this means. Sum of LX column, you just add all of these numbers up and you write that number right there. And so if I did it correctly, we've done this for a lot of years, so I'm assuming it is correctly, you should get 1.09. All right. From here, what you need to do is to make sure you're following these arrows. And so you're going to take 1.09 and subtract 0.65, and that gives you this number. And then you take 0.44 minus 0.225, and that gives you this number. And then, what was that? 0.215 minus 0.12, and that gives you this number. And you continue to do that. Since we summed this column to get this number, and now we're subtracting this column out of it, the bottom two numbers here should always be the same. They should always match, so that when you take 0.005 minus 0.005, it's always going to give you 0. You're always going to zero out that column. This is a great check to make sure that you didn't get off. As you might guess, the most common mistake made on this one is accidentally picking up this number instead of this number. Okay? And it's easy to do, right? Even though we've got it organized into a table to try to make it easier to see what you're doing, it's pretty easy to accidentally pull the wrong number. Right? But it should be the one right next to it, and subtracting 1.09 minus 0.65 gives us the 0.44. Okay? Anybody confused? No? Good. I guess I should tell you TX does have a definition on here, right? It's the number of time units left for all individuals from year X. Again, not going to worry about interpreting what that means. You can remember T for time units, right? That's actually what we're calculating. But we need this in order to do our last column. All right, so once we get our capital LX and our capital TX calculated, we're now ready to do our life expectancy, which is EX. At the very first bullet up there, I have in parentheses, watch your time units. And that's because for some organisms it makes sense to do this by years. So for squirrels, we're doing it by years. But in some of your homework problems, that might not be appropriate. So for example, for the tadpole problem in your homework today, it would be a life stage. Not really time period, but rather a life stage. If we were doing, next week when we're doing exponential growth, we're going to work a problem together. And that problem is going to be fruit flies. So I don't know if you've had fruit flies in your house, but years would not be an appropriate time unit with them. Maybe minutes. I'm kidding, we do days. But they will get out of hand rapidly if you're not careful. And so that's what that's referring to. So watch your time units in the problem and the group of organisms that you're working with so that you know what you have. All right. The next thing you want to do is make sure you're pulling from the correct columns. And so we are using that TX column that we just calculated. But we're going to go back and pick up the lowercase lx numbers in our formula. And so the first one is 1.09 divided by 1, which will give you 1.09. And this is another check place. These two numbers should always be the same. Because on our survivorship, we start with 100% of the organisms alive, so this should always be 1.0. So this number should always match that number. Okay. And then remember, when I ask you to interpret these values, that we're talking about how many years left that they have, how much time into the future that they have. And so a squirrel that survives through year 0, is that how we through 0, is expected to live about 1 more year. 1.09 years if you want to be specific. All right, and then of course the numbers will begin to be different. So make sure you're picking up your numbers from the right column. So 0.44 divided by 0.3 should give you 1.47. 0.215 divided by 0.15 should give you a 1.43, and so forth. And then as our example down here, I pulled E2, so I go to the 2 right here. I pick up the 1.43, and so if a squirrel survives to year 2, it's expected to live 1.43 years into the future, and it has 1.43 years left to live. But something that shows me you know that it's from this time period forward that it's going to be living that long. If that makes sense. Any questions about this particular slide? One of the things, what we're going to be doing next is working with survivorship curves and mortality curves. And if you're following along on Canvas, I flipped some slides yesterday. They're all there though, I just flipped them. I don't know why I haven't flipped them in the past, but we're going to talk about survivorship curves first, and then we're going to talk about mortality. That's the only difference. So I didn't change anything other than change the order of the slides a little bit. But as we talk about survivorship and we talk about mortality, bless you, for sure. Oh, salud, Gesundheit. Anybody know any other? Yeah, Gesundheit's German, salud is Spanish. What now?
Oh, it's Spanish. Okay, salud also means hi in French. So
it's got a D on the end unless I'm missing it. Salud.
Oh yeah, it's like salud, like it's an L-A.
That would be a T on the end. Saw a meme last night making fun of Americans because we can't speak but one language. And mostly that's true. What were we talking about? Oh yeah, life tables. So, when we are making our mortality and survivorship curves, you're going to be drawing them by hand. That's what I expect you to do. I'm going to show you how I do it to try to get you a decent shape on them. But at the end of the day, you need to remember you're drawing them by hand, okay? And so when you start to look at them to try to decide what type of curve you have, you need to do more than look at your graph. You need to also look at the data in your life table to be able to make a good decision. Okay, I'm going to harp on that a lot today. When I give you your homework problems, I try my best to give you a dramatic curve. And so I'm going to try to give you one of these, or one of these, basically. But I also don't want to give you a population that's giant to do your homework, where you have like 30 years worth of data to do by hand. I feel like you might revolt if I did that. And so that makes it really hard, especially to get this, okay? And so if you've got one that's got a little dip in it, what you should do is go back and look at your life table and see what's happening. So before we even talk about the curves, we can look over here at the life expectancy. You can see it's low in the first year. That's not surprising. A lot of the baby squirrels aren't going to survive, right? The juveniles are dumb. They jump off a branch and don't know how to catch the next one. That kind of stuff happens. It's sad, I guess, but it happens. Normal. But if they make it past the first year, they do pretty good, right? Their life expectancy has gone up. They're expected to live another 1.5 years for a couple of years. And then after that, you can see it starts to go down. And what's happening here is the squirrels are aging, right? They're getting to be old squirrels, and then all of them, of course, die, in our life table anyway, before they reach 6 years old, okay? So that's already telling you something about the mortality. We go over here and look at survivorship. You can see it reflected here as well, right? everybody was born, so that's not really what happened between year 0 and 1. It's really more like that's how many we had at the beginning, right? So everybody's alive. But between year 1 and year 2, there's a dramatic decrease in survivorship, right? And again, normal for squirrels and for a lot of wild species. But then it kind of flattens out a little bit before bottoming out. And then the other one we're graphing is the mortality curve. And it's going to start out high, decrease a little bit, and then get higher again, right? For the same reason we're talking about. Dumb baby squirrels, mature squirrels, elderly squirrels, right? Are y'all following along, looking at the numbers? Let's look at the curves. Oh, actually, first we're going to look at the assumptions, then we'll look at the curves. And now that we're all here, I'll close the door so we won't bother people. So as we're building these life tables, remember that we are building static life tables, not dynamic life tables. And so there are some assumptions. Number one is that we age the animals correctly. You need a good method to do that. I've kind of already mentioned that a few times. But even within those methods, there is error. So I'm most familiar with the bluebird since we've been doing that recently. And I told you that one's going to be hard to build much of a life table on because we could just do basically first year and then after. Well, call it second year because it's their second year of life. But less than a year old or more than that is really all we can do from that particular method. But even from that particular method, Dr. Pitts found in his original study when he proposed the method that you can get about 95 to 97% of the birds aged accurately. And then when somebody checked his method, which should happen, so an independent university somewhere else decided to check his method, they were about the same, 97, 98%. And so if you look at the data from our research, I didn't really expect you to have memorized it. But of the 90 birds that we had, we were able to determine sex reliably, and we were comfortable with our decisions for 88 of them. Okay? So there's always going to be a little bit of error in this type of information, and you just need to be aware of it. It's just trying to do the best you can and not forcing. That was a conversation that Vin and I had when they were aging them, not forcing it. Like if it's really unclear, be honest about it and say we can't age this individual, right? So that's what we did. All right. Whoops. Next, we need to make sure that the sample represents the population, the age classes within the population. So we were pretty general on this when we were doing our basics of population demography. We just said pre-reproductive, reproductive, and post-reproductive, right? That's all we really did. But this is what it's referring to. And so we need to know that the number of individuals in the squirrel age class 0 to 1 and 2 to 3 and so forth really represent what's in the wild population. This can be a problem when you're basing your life tables on check station information. Why is that the case?
Because they're only taking individuals of certain.
They're not taking individuals randomly, right?
Yeah.
And so if you want to get a random sample, that's going to give you a better estimate of what's going to be in each of these age classes. But a lot of times at check stations, they're not shooting randomly. They want something in particular. Right? And so you have to keep that in mind. It doesn't invalidate your life table. It's just a bias that you need to be aware of, depending on what group of organisms you're working with. All right?
Plus, even if they weren't grouped yearly, they still, at least in my experience, tends to be the younger portion of the population, because the older the deer is, the more experienced it is and not getting shot.
A lot of times they're after the older ones because they have the larger racks, right?
Right.
You got the 3 things that give you big racks. Sales of wildlife major 2. Mm-hmm. Age, nutrition, genetics, right? They hammer it into like every class I took. That's been 30 years and I can still tell you those, right? And so that kind of plays against you a little bit. But it also depends on the experience of the hunter. I was working a check station at Reelfoot 30 years ago. And y'all know where the Walnut Log Road area is? When I was in school, that was a gravel road. And we were down at the end of there, and they were hunting back in there. And there was a couple of men from Memphis that came up to hunt. I guess they drew and were able to get on the wildlife refuge. And they came out in this huge Jeep with just a spotted fawn on their hood. And they're like, we killed deer, you know. And so that was just, they shot the first thing they saw.
Yeah.
Right? And so there's some of that happens, but more experienced hunters are probably already out looking for the deer they want, right? They know what area it's hanging out in. They're waiting for the hunting season to start, and then they'll go get that deer, right?
Yeah, I just know.
My dad was a deer hunter, so I do know a little bit.
I don't think I've ever like aged one over 4 working CWD check station, so it's just something like this.
There's other things that affect deer besides just hunting them. Whoops, we didn't talk about able state. All right, so this one is harder to figure out from a sample, but basically it's saying that your ratio of your different age classes, I'll just stay simple for now, so your ratio of pre-reproductive to reproductive to post-reproductive is not changing. It's the same this year as it'll be next year as it'll be the next year. Okay? That may or may not be true in the population. You know, if we're in a fairly stable time and we haven't had a severe drought or a severe winter, then you might actually get something like that. But the reality is that environmental factors do tend to come into play, and they do tend to affect these populations. Some of them, you know, might be able to affect across all age groups and keep you stable. Others probably not. But anyway, that is one of the assumptions. The next assumption is we assume that the growth rate is 0. In other words, the population is not growing. And this is kind of getting at the same type of issue, because if your population is growing, that means that you have a wide base, and your base could continue to widen. And so if it's actually growing, then that will change your ratio between your age groups again. Okay, so that's kind of the reasoning as to why. And so if you think about what a static life table represents, then especially those last 3, all but the first one, makes sense, because a static life table is a snapshot, right? It is a single period in time that you took a sample and you put that information into the life table. And so it's not accounting for anything that might be changing from one year to the next. If you want to do a life table situation in which it is changing from one year to the next, then you're going to have to go to a dynamic life table where you're putting multiple cohorts in and looking at it that way. If you're working for an agency, like I said, I'm having you do what you need to do to learn how these things work to calculate these simple life tables. But if you're working for an agency, you're going to take that harvest information and put it into a database, and you're not going to be making your decisions based on a single year's information. Does that make sense? So I want to give you the practical angle on it. Okay, so that's the assumptions. Any questions about the assumptions? All right, I said I flipped this around, and so I'm going to survivorship first this time and see if that helps us out a little bit. And then we'll do mortality. All right, there are at least 3 hypothetical types of survivorship curves. You don't have to worry about the at least part. We're just going to do 3. And you may have run into these before, but if not, we'll go over them. We're going to try to define them pretty carefully, and then as you're doing your homework, anytime I ask you what type of survivorship curve is this, I'm going to expect you to give me a representation of what's happening in that curve. In other words, pay attention to these slides. Right? That's all I'm really saying. The first type of curve is our type 1. It's convex. And so that was the one where I'm going to try to give you a good dip. So I'm going to try to keep it really high and then make it drop off like this picture. And this is typical of populations where individuals tend to have good survivorship throughout their life. They live out their physiological lifespan and then they die. So that tends to be pretty typical of humans, for example. We have pretty good survivorship, even better than this. We've even flatter than this. Until we get out to about the 80s and 90s. People that are 80s and 90s, and then you start to see it plummet. And then once you get past 100, we're going to eventually go down to 0. We don't have very many people who live past 100 to 105. Did you see Jimmy Carter turned 100 yesterday? It was yesterday. Wow. It's pretty impressive. I guess building houses is good for your health. I don't know very many people that are 100 personally.
So he was the first president born in a hospital.
I saw he's the first president to reach 100, so he's also the first one born in a hospital. That's interesting.
Yeah, that old.
Okay. Before we leave this one, if we were looking at other species, like if we were in a general ecology class, it would show trees, for example. But what I want to point out is in a natural population, and I'm not going to give you a natural population on your homework, I'm just going to give you a fake one, of course, but in a natural population, what you would generally see would be a dip and then flatten out. What's causing that dip? Yeah, you know, generally speaking, you are going to have high die-off in your juvenile phase, whatever that happens to be, right? So if we're looking at an oak tree, most of the acorns aren't going to survive, right? But the oak trees that establish themselves, they're going to live out their physiological lifespan and then die, right? So that's what I'm getting at. If we looked at elephants, I don't know how bad their die-off is. I think I've seen like probably a fake graph in a textbook, but it does the same thing. It's a little bit of a drop within that first year, maybe first couple of years, and then it flattens out and they do their physiological lifespan. So that's just a note. That's typically what's going to happen in reality in a wild population, is you're still going to have the dumb squirrel effect, right, where they jump and they miss a branch and fall to their death, that kind of thing.
Like tried to actually run from your car.
What now?
Or they actually tried to run from your car, but it was all lost.
They just make bad decisions. All right, any questions about type 1? All right, type 2 is linear. But if you look carefully at that line, it also isn't perfectly straight. I would say that's pretty typical. It's really hard to get a straight line, exact straight line. All right, this is the one that I typically have the most difficulty pounding into your brains for some reason, but I'm going to try. I'm going to try to pound it in there. Anyway, this is organisms that tend to have a constant mortality rate, and by reverse, a constant survivorship. So kind of glass half full, half empty, whichever way you want to go. Their odds of dying is about the same at every age class. A classic example of this is actually birds. Birds are pretty fragile overall. And so, kind of like I was saying on the last one, generally it's not going to be a perfectly straight line. You'll have a die-off at the beginning. Birds have a pretty good die-off in terms of egg to fledgling to adult. But if they make it to the adult stage, then they're pretty type 2. They fit it pretty well. And there's a variety of factors that's probably impacting that. For example, they lay their eggs outside their body, and then both the male and female try to protect it, so they're both up for predation when that happens. Migration is a big cutting of the population. It's probably not the right word. So right now I was listening to the birding podcast. Y'all listen to that, right, every week? American Birding Podcast. And they were talking about what do you enjoy about the fall migration, and I wanted to say nothing, personally, which is not completely true. But the birds are not in their breeding plumages. It's harder to identify them. They're a little bit more secretive. They don't come through in a big wave like they do in the spring. They come through in several smaller waves. And one of the people in the podcast was kind of like me. They're like, well, for me, my favorite part is the weather changing. That's what I'm saying. I love the fall, but I don't bird that much in the fall. But what they were pointing out is that's when all of the bird populations are at their maximum. And so even though it's not as exciting as spring migration, there's actually way more birds as a whole moving. But a big chunk of them are going to die on their first migration. And then a big chunk of them will die on the migration back. And then, of course, they'll have to replenish the population next summer. And so in the spring, if some of you go off and work with the public, you'll get a lot of, I haven't seen a hummingbird for like 2 months in the spring. It happens every year on all the little birding groups. Is where are my hummingbirds? Do you have hummingbirds yet? Have you seen a hummingbird? That kind of thing. And what's happening is the population's very low. Those guys fly across the Gulf of Mexico nonstop. That's very dangerous. And if the wind shifts on them while they're doing that, they fall into the ocean and die. Sometimes they can't gain altitude and a fish will come up and just grab them. There's a lot of things that happen. And so their population is at the smallest at spring migration. But in October, September, August, the population of hummingbirds at my bird feeders at my house is ridiculous, right? That's when the population's at its maximum. So anyway, those are the types of factors that are causing the birds to be type 2, and whereas other species typically are not. It's not the most common pattern by any means. The most common pattern is going to be the next slide, but there are a lot of bird species that are pretty close to type 2. All right, any questions about type 2? Okay, so our last survivorship curve is type 3. And in type 3, this is where you're going to have a lot of mortality in the juvenile phase. But if they can become smarter and learn how to jump from branch to branch more intelligently, learn how to gather food, learn how to avoid predators, then they'll tend to live out their physiological lifespan. So a lot of mortality early in life, and then those survivors live out their life. The ones that make it through. Also called natural selection, right? All right, so that's our 3 types of survivorship. And like I said, type 3 is pretty common. And so without graphing the data, which we will in just a second, but without graphing the data, what do you think the squirrels are going to follow? They're going to be type 3. Yeah. Fairly high mortality the first couple of years, and then those that make it live out their physiological lifespan.
Would that go with like pretty much like most creatures that tend to have like really large like litter sizes or like lay like a lot of eggs?
Yeah, I mean, this is going to get a lot of species are going to fall into this one. Like type 1 is going to be your longer lived things. And so while many birds are type 2, you can think about some of the ones that have like bald eagles that don't reach maturity till 5. They're going to be at least closer to type 1 than type 2. And by saying that, what I'm really telling you is life out there is a spectrum. Remember that it started out with there are at least 3 hypothetical models. And the reality is they're not going to match these hypothetical models exactly. But that doesn't make them useless because it tells us quite a bit about what's to expect in a population going forward. And especially if we have some event that knocks that population back, how fast it might recover, and some other information like that. Okay? All right, so here's a graph showing you all 3 on the same graph so you can see. Notice we've got age, and we're not going to have survivors. That's what they have here for some reason. We'll be doing survivorship. We're going to graph the LX, and so we'll be more specific than that. But that just kind of gives them all together for you to look at. And again, reminder to, when you build your own curve, to look at the data and not just rely on eyeballing the shape of your curve. All right? I don't really have a lot to say about that slide other than you can see all 3 together. And you got definitions of them again. All right, so for the gray squirrel, we'll start there. The way I typically do this is both of them, both the survivorship and your mortality are going to have a scale that goes to 1. Okay, so that makes it a little bit easier to divide up your scale. And so let's start with our survivorship curve. Here I'm just reminding you, as we're pulling out X, we're going to go with the beginning year for each one of these. And so we've got 0, 1, 2, 3, 4, 5, and 6. Okay. The 0 is always going to be where the X and Y cross, right? So that's 0. 1, 2, 3, 4, 5, and 6. There we go. And then typically what I'll do is I'll go to my top up here, and that'll be my 1.0, and then I'll kind of eyeball the middle and make that my 0.5. I've also done this a lot. Not perfect, of course, but good enough for eyeballing. Oops, I didn't do that one right. Oh yeah, I did. I just too high on my 0.6. There we go. There we go. Got them all on. No, you did perfect.
Oh, really?
You didn't lock yourself out. You're good. All right, so now we just have to make a graph. We're going to make a line graph, not a bar chart like my freshman would try. And so it's 0. Everybody was born, right? Everybody's alive, and so it's always going to be 1.0. Okay. And then as we get to their first full year of life, so year 1 to 2, we've already dropped to 0.3. And then we drop in half again to 0.15, so that's about right there. And then we drop to 0.09, not right there. 0.04, ooh, it's getting on down there, about right here maybe. 0.1, that's going to be around the line, but not at 0 because that's 6. All right. Then you connect up your dots, try to be as neat as you can. There we go. And so here's my survivorship curve. What am I missing? How am I going to get all my points on my homework?
Your life.
I'm missing down here, right? So my age. And what are my units on my age?
Years.
Year. And then over here.
Survivorship.
And what do we actually graph? Yeah, lowercase LX. That's what we're actually graphing. So don't forget to label your axes. Oops. I just figured this. And this is pretty typical of when I try to build this one. So what we've already said, but what type of curve is it? Type 3. And what does that mean?
High death rate.
Yeah, have high mortality in the first year, and then the ones that survive through that live out their physiological lifespan. All right, anybody get lost on how I put my curve together? Sure my lines are. Nope, I'm good. 9.5 for me. I didn't label one of my axes on my homework. All right, I don't know. Don't worry, I still got 8. So I did it like this because that's the way you're going to do it. You're going to do it by hand. I wanted to show you how you can kind of do that. But I do have it in your graph, an actual graph in your notes. So this is what it looks like. Nothing unusual here. Looks a lot like what I drew over here. Any questions about survivorship curves and drawing those? Yep.
When you ask us about it, do you want us to say like type 1, type 2, type 3, or just convex, concave, or linear?
Type 1, type 2, or type 3. Those are actual names. Yeah. But when I say why, if you want to say because it is convex, concave, or linear, in the context of your explanation, that would be probably good, but not necessary. Mostly I'm looking for that high mortality early in life and survived until and then lived out their physiological lifespan is mostly what I'm looking for. Okay. Anything else? Questions? Good. Get us on the same page. While we all speak English, we don't all think the same. All right, and there's a lot of stuff in my brain. And a lot of stuff in y'all's brains. All right, mortality curves. Okay, in this case, we are going to plot the QX, not the LX. And usually it consists of 2 parts. That juvenile phase where you have high mortality. A post-juvenile phase where mortality is a little bit lower. And then I'm always feel like the mortality discussion in the textbooks is misleading. Because then, of course, you're going to have higher mortality. So that's really the next phase, right? When you live out your lifespan. And so it's not like the mortality is going to fall and stay low. It's going to go back up as they age. And we'll see that when we look at our curves. So I'm just kind of giving you a heads up on that. So this is kind of your textbook slide. And then as we look and see what happens with different types of survivorship curves, you're going to see that that greatly impacts what your mortality curve looks like, is what I'm getting at. The mortality curve for gray squirrels is textbook. Right, and that's where we're going to start. All right. Hopefully that'll make sense as we talk about this a little bit. The first thing you'll notice is I got highlighted our X and our QX, which is what we're going to graph. But last time, I warned you greatly, we don't use the 0 here because this 1 represents that everybody in the population has died, so 100% mortality. And so if you go from 1 back to 0, everybody's alive again. It's an exaggeration, but that is basically what it's saying, right? So you had 0% mortality, but the reality is they're not coming back to life. You just didn't have anybody to die. But it's more fun to say you have zombie squirrels if you put the 0 on. Okay? Which means I need to adjust my axis a little bit. So I'm going to take off. I'm just going to take off. Why did I have to take that off? I guess. I'm going to take this axis off because now we just need 1, 2, 3, 4, 5. So 0, 1, 2, 3, 4, 5. It's still the age. Oops. In years. Instead of survivorship, though, this is our mortality curve. And specifically, we're doing the lowercase qx. There we go. And then just do what we did last time. So this one starts at 0.7. And then it drops to 0.5. 0.4. 0.55, so it's starting to go up again. 0.75, and then 1.0. Connect them up. Okay. All right. Do that one a little bit faster. Y'all seem fairly competent. So this is, like I said, kind of what they're talking about. They're classic, where you have a juvenile phase, where you have where you have high mortality, and then you have kind of your adult phase, where you have lower mortality. And then what I'm saying is there's really one more, right? And that's when they age out up here. And so let me get the actual curve. It looks like this. Although I left my 6 on that one. Most common mistake I see on these is to go on out to 6, which would make it a 0. And people doing this, that doesn't make sense. So that's where I'm like, just on a lot of this, just stop for a minute and it'll make sense. You shouldn't do that. All right, so that doesn't make any sense. Take that back off. Don't do that, or you get a big X on it. The survivorship curves, I'm going to try to give you good shapes. Like I said, one of the main hints that you're going to have a type 2. By definition, type 2 has constant mortality across all age groups until they age out, right? And so if you end up with a mortality curve that looks like this, that's going to be type 2, right? Type 1 is not going to have a deep curve like this either. It's going to look a little bit different. But the hardest, y'all tend to do pretty good on that because I try to make it very dramatic. So we don't usually struggle with a type 1 and a type 3. We're struggling with that type 2 in the middle. Okay? You can also tell that you have type 2 mortality if you just look at the raw data, because the closest I can come to do it is we start out with a population of 100, and then we go to 50, and then we go to 25. In other words, I'm decreasing by half every time. Okay? That's what's going to give you type 2. So there should be lots of hints. And so if you end up with a survivorship curve that looks like that, or maybe it looks a little bit like this, it's not dramatic. What I'm trying to do is to give you that. Okay? So I'm just kind of warning you. But even the example in your homework shows that it's not going to be a perfectly straight line in your notes. Any questions about any of that? Okay. All right, any questions about anything in this PowerPoint? Okay. Okay. Y'all already got your homework. Everybody have your homework? I forgot I told you to pick it up. All right, that's where you're at. I have the answers right here. Okay. I will say, and I didn't.